Thank you. Hello, Insomniac. Welcome to my session. I'm Maor Abutbul, a vulnerability researcher at CyberArk Labs. Thank you for having me, and thank you for coming. I'll start with a question. What would you think if I told you that your identity could be held by your system admin? That's trivial, right? But what if I told you that your identity could be mine or any user on your identity provider? That's scary, right? By the end of this session, you will find out how. In this session, I'm sharing not only success stories, but also tools and techniques, rabbit holes, and failures. You may ask why, because these are great learning opportunities. We'll start with the GET request. So, who am I? I'm Maor Abutbul, a father, engineer, gamer, researcher, and gamer. Rumor has it, I'm not the only gamer here. Around 8 years ago, I transitioned from engineering to research. Today, I'm a vulnerability researcher at CyberArk Labs. My team's main focus on open source and identity-related systems. We share our work internally to make our products more secure, and externally via blog posts and talks to give back to the security community. Our main agenda for today. I will highlight key items from 2 research projects we did on 2 open source identity providers, Keycloak and Authentik. Each part will start with a technical background to set a common ground for everyone, and then a deep dive into a technique or a vulnerability. I will also share short demos exploiting the vulnerabilities we found. Part 1. Keycloak research and web race conditions. We'll start with some technical background. So, what is an identity provider? An identity provider is a system that creates and manages digital identities. In our case, users. The IDP handles managing users, from user creation and login pages to enforcing password policies, making the developer's life easier. By integrating with an IDP, you don't need to manage users or store their password and expiry. The IDP manages it for you. Multithreading. Multithreading is a programming concept that allows multiple tasks to run concurrently on a single process. In the web context, web servers use multithreading to process multiple requests simultaneously. Web race conditions. Let's define the problem. Web servers process requests concurrently, and because of multiple threads interacting with the same data at the same time can cause unintended behavior in the application. Limit overrun race conditions. The most well-known type of web race conditions. It enables you to exceed some kind of limit imposed by the business logic of the application. Examples will be redeeming a gift card multiple times, or withdrawing or transferring cash over your balance. We'll start with an example logic. This is our example logic. A request arrives with a discount code. The code is verified, and since it's not used yet, it will be accepted and applied. We also set the variable to used. Then later, a second request arrives with the same discount code. This time, the request will be rejected. From a timeline view, the first request arrives, accepted, then the second request arrives and rejected. This is the expected behavior. Let's look at the same requests in the race flow. In the race flow, both of the requests arrive at the same time, and because of concurrency, they are processed at the same time. In this time window, the code used variable is not set yet, so both of the requests are accepted, leading to the code being accepted twice. The time between the check and the update is called the race window. In this race window, we can exploit this issue. So, how can we test remote servers for race conditions? The single packet attack. The single packet attack is a technique developed by Potswiger. It allows packaging or encapsulating multiple requests on a single TCP packet. Generally speaking, the algorithm collects all of the relevant requests, sends most of the data without the last bytes, waits for a few milliseconds, and then sends the last bytes in frame. The single packet attack algorithm, I don't care. Show me how. To use the single packet attack technique, there are a few tools we can use: Burp Repeater, Turbo Intruder, and more. Today we will cover the first option, using Burp Repeater. We start by sending our request to Burp Repeater. Then we edit the requests. Within the repeater, we can create a new tab group. This group are requests to be sent together. Then on the arrow near the send button, we can select send group in parallel, the single packet attack. And that's it. Now you can test web applications for race conditions. Single packet, many requests on a single packet. Come on. They didn't fit me. From what I know, in HTTP version 1, if we send multiple requests, all of the requests are sent on the same stream. So if we send multiple requests, they will just get mixed and the server won't be able to pass it. Then I was thinking to myself, it would be cool to inspect the traffic in Wireshark. Not so fast. The single packet attack is an HTTP version 2 only mechanism. HTTP version 2 uses TLS. Okay, so let's decrypt. This took us into a journey in which, in the end, we found the following tool. Using this tool, we could extract the relevant secrets, and then, we have the secrets. Let's inspect some packets. We'll start by inspecting HTTP version 1 traffic. In HTTP version 1, the data is transferred in clear text, so the content is ASCII encoded. As can be seen in the image, the literal characters GET are ASCII encoded on the wire. In HTTP version 2, messages are called frames. The data is transferred in binary. As can be seen in the image, after decryption, the GET method is translated to the 82X value. In HTTP version 2, a new feature was introduced called multiplexing. Each frame has stream ID. These IDs represent different channels in which can distinguish different messages sent. This feature also allows sending multiple frames on the same packet. Let's inspect the single packet attack. As can be seen in the image, the single packet attack is used to send 3 different GET requests in one packet. HTTP takeaways. HTTP version 2 is binary using frames and streams. Using streams permit multiple requests and responses to be sent simultaneously. This feature allows the single packet attack to work. Let's evaluate our learned methods on Keycloak. Our first target, Keycloak, is an open source identity provider maintained by Red Hat. It's the upstream of Red Hat single sign-on. Let's dive into our first story. Everything is multi-step. Here, our journey started by inspecting the Keycloak database. We found out that the users table is separated from the required actions table. As can be seen in the image, the verify email flag is maintained in a separate table. This means that on creation, no email verification is needed. So we speculated, can we gain unauthorized access by using an arbitrary email? This means that if we create a registration request and a login request at the same time, in this time window, we could log in without email verification. Let's inspect the user creation code. As can be seen in the snippet, first, a user is created. Then later in the code, the required action is updated. This is our race window. So if we time it right, we can register and log in with an arbitrary email, and hopefully an admin. Let's race against user creation. This test required us to create some burp macros, which allowed us to create a user and login request at the same time, at the same packet. We worked with the debugger, stopping at the relevant code, then checked the database directly, with no success. We failed. We lost the race against user creation. We lost the race, but this seems like a great opportunity to understand why, and more importantly, to learn how to avoid race conditions. So, using debugger breakpoints and activating ORM logs, we found the missing piece. In the logs, we see the following 4 key items: auto-commit disabled, insert into users table, insert into required actions tables, commit. Auto-commit disabled means that the application is using transactions. Transactions means the database is updated in one shot or not. So in this case, transactions prevented us from gaining unauthorized access. With race conditions, everything is multi-step. Well, sometimes. But now we know how to find and avoid race conditions. Okay, let's move on to our first demo. We'll start with some background for the demo. In Keycloak, an admin can create API keys for developer to use on the system. On creation, an admin can limit the number of clients that can be created by the developers. In this case, he set it to 2. The developer uses this token while creating clients via the Keycloak API. After using this API, the token's remaining count is updated. A moment, and we'll inspect the demo. Okay, we started creating a realm, which is a tenant or an organizational unit. Then we create an initial access token and set the limit to 2. Now we send this API token to the developer. The developer using this API token to make a client creation request, and he also send this request to his bare proxy. So one client was created, client 1000. We'll now send the request to the repeater and modify the request. We'll create a few requests in the repeater. We just modify the client ID 1001 to 1004, and later we will group them together. Now we will create a new tab group, select the relevant requests, and just give it a name. And we will send them together. Send group in parallel and send. Now let's see how many clients were created using this key, and 5 clients were created using this API key. And if we check the remaining count, we have a negative number. So at least math they know. In case you missed it, we were able to create 5 different clients using an API token that was limited to create only 2. So to summarize this part, we reported the issue to the to the Keycloak team. They confirmed it, made it public, and fixed it. Keycloak research takeaways. HTTP request processing isn't atomic. HTTP version 2 is binary, using streams and frames. The single packet attack can be used to test web applications for race conditions. The same system can include overlooked areas for race conditions, as we see in the regular request and the API request. Okay, that's it for this part. If you are interested in learning more about this research, check out our blog post. You can't always win racing the Keycloak. In the blog, I cover these race conditions and more. Okay, let's dive to our next part, Authentic research and ORM leaks. In this part, we start with a short technical background, then a deep dive into 2 vulnerabilities we found on Authentic. Let's get started. Object relational mappers. ORMs are a programming technique used to convey data between relational databases and object-oriented programming language. They allow you to manage data without using SQL queries. In ORMs, models define the structure of stored data. In the image, we can see an example of a Django model declaration. The Django is a Python framework that includes an ORM. So, our new target, Authentic, is an open source identity provider maintained by Authentik.io. Note, Authentic is a Django project. We will now dive into our first Authentic vulnerability, sensitive information leak. We'll start with some background for this part. In Authentic, certificate can be used for 2 main functions. The certificate that is attached to the Authentic web server itself, used for HTTPS communication, and when configured as an identity provider, to sign auth tokens. Here, our journey started with an admin user. An admin can upload and generate certificates. Admin can also download certificates and private keys. So far, all good. At this point, we speculated, can a user download the certificate? So we tried, and whoops, we found that not only any user can download it, no authorization is required at all. So anyone can download the private key. But we do have a limitation here. The internal UUID set by the Authentik server itself is required for this request. Here we were thinking, how hard can it be to leak a UUID? But before we dive into this question, let's see if we should care. So, a private key can be leaked. Should we care? An attacker possessing the private key can impersonate the Authentik web server and by that phish users or admins. An attacker possessing private keys can also impersonate tokens and by that gaining access to any system trusting Authentik. So, with our motivation set, let's get back to our question. How hard can it be to leak a UUID? This question took us into the rabbit hole. At this part of the research, we already knew there are many API endpoints in the system. We noticed that some API calls are leaking some internal UUIDs. We suspected there must be one API in which we could leak this data. We are looking for direct leaks from the API, requesting each API in the specification. This attempt failed. Then we encountered an excellent article by Eltam. Defined a new class of vulnerability, namely ORM leaks. This article is about how insecure use of ORMs can lead to information leaks. In my words, this technique allows attackers to leak data like SQL injections, but provided by the ORM. So, to find ORM leaks in Django, the pattern we are looking for is using the filter method with the unpacking operator, double asterisk, applied to user-supplied data, allowing us to leak some internal data and hopefully our UUID. So, we were looking and we found a promising ORM leak in the event logs API. This API endpoint can be accessed by any Authentik user. Okay, so we found a random API. What is it about anyway? This API returns timestamps and values. Each value represents the number of occurrences of a log entry in the relevant time slot. It is used by the Authentik UI, Events UI, to show event hits in each time slot. Okay, so we have an event log leak. Is it relevant for us? While inspecting the events log, we found the following entry. When admin uploads the certificates, the certificate UUID is get logged in the event log. Notice that the key data is masked here. We can't leak it from here. Let's try to exploit the ORM leak. Here's a typical request to the leaking event API. If a log entry is found, a non-zero value is returned. So we update the request to include a regex query to exploit the ORM leak. When using this regex request, notice the response. If the number if the response includes a number different than 0, we found a log entry. So with this API behavior, we have an oracle. Let's inspect the demo. Using this oracle, we were able to leak each next character from the API and eventually the full UID and the private key. After exploiting this issue, creating a POC, we tried to request it using a normal user permissions, but this attempt failed. We found that permissions are required in the database. To summarize this part, we reported the info leak issue to Authentik team. They confirmed it, assigned CVE, and fixed it. And now, as promised, Authentik privilege escalation. Here, our journey started as a non-admin user. Logging in as a non-admin user. Then we encountered this functionality. A user can create API tokens for himself to use it to access the API. So we created a token, and we noticed that each token has expiration date. A user can copy the API token. A user can also edit his tokens. Here, edit means update. So a user can modify the token's description, and by default, the expiration is updated. This seems weird to us, so we decided to inspect this update request. When updating the token, we noticed an interesting JSON key in the response, the user object. That led us thinking, what if we try to update the user? So we added the user key and set the value to 6. This request returns a valid response, and the user key is updated. Let's look at the demo. We will start by logging in with a normal user. We'll copy the cookies and the CSRF token so we can make requests from burp. We now create token for this user, a regular user, and we will get the token's value. Now we will verify that the token is active, and it's active. We'll now change the request to put, and we'll update and add the user JSON key and value, and set it to 6. This request seems to work, so let's try another Maor API request. Set password. Let's see if we can log in. So the API returned us the username, and we set the password. Will it work? So we have admin access to the system. We have admin API key. We have full control of the system. To summarize this part, we reported this issue to Authentik security team. They confirmed it, assigned CV, and fixed it. Let's conclude our session. In part 1, we covered our Keycloak research. We started with a technical background on IDPs and multithreading. Then we covered web-based conditions and the single packet attack and HTTP version 2. Lastly, we evaluated our technique on Keycloak. In part 2, we started with the technical background on ORMs, then got into the private key information leak and ORM leaks, and then we concluded with our authentic privilege escalation and demo. Research takeaways. HTTP processing isn't atomic. HTTP version 2 is binary, using frames and streams. The single packet attack can be used to test web applications for race conditions. For developers, ensure sensitive endpoints make state changes atomic in the API as well. Double-check access restrictions on sensitive endpoints, certificates, and so on. Avoid direct manipulations of API tokens, generally tokens. When using ORMs, be aware of vulnerable patterns and safe use. Oh, one more thing. In Authentik, when logging with an admin privileges, we found an interesting functionality. Built-in impersonation. This functionality allows the admin to log in as any user in the system. So, your identity is mine, or any user from your identity provider. Thank you.
So I guess we have a few minutes for questions. Any questions?
Hi, thank you for the interesting topic. Just out of curiosity, do you remember how much time it took to Authentik to patch the vulnerabilities after you reported?
Authentik specifically?
Yeah.
Okay. It was pretty fast. I think no more than 2 weeks.
Okay. Thank you.
Thank you very much. I have a question. In the last vulnerability, you showed that you changed the password of the admin, but effectively the token that you had admin permissions. Was that showing up on the admin console, or it was not seen by? Was it hidden?
Okay. When you change the token itself, it is you change the who is it belong to. So the token was belonging to the admin at that case, yeah. Okay. And because we took the API key before, we had access to using this.
Yeah, thank you.
Okay. Any other hands?
Thank you very much for the talk. I was wondering then, in the Keycloak case, since you needed database credentials, did you get a full chain, or did you just stop there and report the vulnerability?
In Keycloak?
Yes.
No, it just was a bypass of a limit that was imposed by the system. It didn't go to privilege escalation. Just admin could create more clients than they should have. Sorry, not admin, developers.
Okay, looks like we have no more questions. Thank you, Maor.
Thank you.